welcome to lecture 9, and as I told you that so far we have considered networks involving only resistance as circuit elements and also sources, both voltage and current sources, but they are not varying with time, that is they are DC quantities, constant values. For example, see the previous networks, all batteries fixed voltage and only resistances are present. Similarly, there were examples with current sources that we have done fixed current sources of certain value. But now we will go ahead with I should be in a position that the circuit may, as I told you, can contain in general resistance, inductance and capacitance, and also the sources may be time varying sources. Okay. So, first resistive elements, let us try to understand. Here is a resistance and the current in this direction, which henceforth, because I am not sure, in general current may be time varying quantities. So, we will indicate any time varying current as this one IT. I do not know, sources may be time varying, and the direction of the current, as I told you, is my prerogative. I will choose it. But once I choose it, I know the potential of VAB, that is, if A, this is point A, resistance 2 terminals, then VAB we will indicate it by plus. Wherever I write plus henceforth, it means potential of this point with respect to this. So, you can see the voltage current relationship of a resistance is will be equal to VAB, which may be also function of time, I do not know, and that is resistance. So, at any instant of time, calculate potential of A with respect to B, divide by R, you will get current in this direction, that is very important. So, once you have assumed the direction of the current, this will be plus minus, and this is called the terminal VI relations. So, small letters we generally are used for any time varying quantity, I do not care. So, VABT, and this is also sometimes written as, instead of writing VAB, you can also write it as V if you indicate only plus and minus. So, V is potential of this with respect to that, it means that. So, VAB is VT divided by R. So, this is this thing. Now, obviously, this VT, applied voltage across the resistance, as I told you, could be any function of time, no restriction. I will now put that it is a constant quantity. For example, VAB could be this shape, this is my VAB, this is how VAB, and this is my axis time. So far, I have considered for DC quantities, it was like this. Voltage was constant E, some V. But I am now telling this voltage could be, so this axis is voltage across time. It is a special case of time varying voltage, where it is constant at all the time. But here you see, at this time voltage is this much and so on. It varies with time, sometimes it becomes 0, it may become negative also, it does not matter. Then what will be the current in a resistance? current in the resistance will be some constant in 2 V t. Therefore, the current, if you sketch for this applied voltage, and I will sketch it against time for a resistive network, it will be also of same shape, because V t by R, V t is this and this is equal to V t. If you write only V t, you must show what is called plus minus, potential of plus with respect to minus. So, this is V t. So, the shape of the current will be also like this. This is I t and this will be V t by R, scaled down by some number. So, this will be the simplest case. So, if the voltage is of any form, current will be also of same form, because 1 by R. Okay. So, this is the story of resistive network, and also we should remember that in a resistance power loss, power is voltage into current, and V is equal to R I. So, this is same as R I square. Now, this power will be lost, and resistance always receives power and it dissipates it in the neighborhood. Therefore, it will be power will be lost, whatever power you input to a resistance, that gets immediately dissipated as heat. Therefore, it is not an energy storing element. And another thing, this equation, if you look at it carefully, it is needless to say that the value of the current at a given time, for example, at this time, at this particular time t equal to tau, what will be the value of the current? Value of the current will depend only on this value of the voltage, this V divided by R, R is a constant number. Therefore, a resistance current at a given time will depend only on the magnitude of the voltage at that time existing. It does not depend on the previous value nor on the future values. So, current value of the voltage divided by current value of the voltage divided by resistance gives you the current value of the current, I mean present value of the current. Got the point? It does not depend on the previous voltage, things like that. What is the right now? What is the voltage? That voltage divided by R will give you right now what is the current. That is the whole idea. So, this is about resistance. That is why resistance are called, a term I am writing and which we can easily appreciate. Resistance is a memory-less device. Memory-less element. That is, resistance does not remember how you treated that resistance with previous voltages. Present now, what current value it will return to you depends only on the what is the current or present value of the voltage. It does not care what happened earlier to this resistance, what kind of voltages you applied, it forgets that. It will only respond, okay, what is the voltage across me right now? Based on that, current value is decided. So, it is often called memory less element, it does not remember, and all the powers and resistance will always receive energy. There will be no situations when actual value of the current will be like that. That is negative resistance, we are not dealing with that. It will never deliver current to your circuit. Resistance is a dissipative element, this you must remember. Anyway, now let us come to an inductive circuit. So, this is the voltage current relationship. So, this diagram is important, this diagram always you keep it in your mind, and this is the thing. Now, let us see what is an inductor. Which is denoted by L. Okay. And now, inductance will be represented by this symbol. L, and a value will be written whose unit is Henry. R is in ohms and it is in Henry. Now, if you apply a voltage across it, that is V, and if you want to write with respect to potential difference, we understand, since I have written plus, we are telling that I am concerned about this voltage VAB I have applied, and current I will always assume it is entering through the plus. Then the voltage across this inductance VABT, and small letters, let it be time varying, I do not care. So, VABT at any instant, what is the voltage across the inductance will be L di dt, and the polarity of the voltage is plus and minus, like that, through whichever terminal current is entering, that will be the plus sign of this voltage. Okay. Or if this is plus minus, you assume, that is, we are assuming two things. One is direction of the current I have assumed, and di dt is positive. That is why this is the convention I will be following, and everybody follows that. Now, the question is inductance as such, I will just tell a few words about that. Inductance is generally manufactured with some magnetic core and some turns are wound like that, and if you pass some current I say DC current you pass, then there will be some flux produced inside the core of this magnetic material. Then inductance is defined as flux linkage per unit ampere. That is, if you pass I ampere, calculate what is the flux linkage. That is, if n is the number of turns, it will be n phi by I. If you pass 1 ampere current, what is the flux linkage? That is Weber turns. So, its unit, basic unit is Weber, flux is Weber, Weber turns per ampere, and this is called Henry, 1 Henry inductance. Whatever comes out, that much Henry it will be. That is, if you pass 1 ampere current, if the flux linkage is also 1 Weber turns, then it is an 1 Henry inductor. Anyway, this is the thing. And to find out and if you wish how physically it will depend, you can write it several in any book you consider. Phi is nothing but flux density into cross sectional area of this magnetic path. So, phi is B into A by I. Then if you assume linear magnetic circuit, that is what, if you want to get a constant magnitude inductance, then we know, so L is this, and B is equal to mu 0 mu r into H. This we know from magnetic circuit. So, put this value B A, I wrote I 2 times. So, this is the thing, n phi by I. Now, this will then becomes n by I into A, and B you can write it as mu 0 mu r into H. But you know that value of H is N I by L. What is L? L is the mean length of the flux path. This we know, I will assume, we will not go into detail. So, this length is L. So, write it down. So, L becomes then N A by I, then mu 0 mu r, these are permeabilities of this one, and this is N I by L. Therefore, inductance, this I will then cancel here, and you will be left with inductance L is as mu 0 mu r, then n square, then A by L. So, you see, inductance is a value attached to a coil which does not depend upon the magnitude of the current flowing. Like this formula for a resistance, we know whether you are passing a current or not, the resistance value is rho L by A. It depends upon the physical dimension of the wire, is not? L is the length of the wire, A is the cross sectional area, rho is the resistivity. So, similar to that, this is the formula for inductance, which is a constant number provided mu r is a constant value, that is B H curve is linear. Anyway, we will not go much beyond this. So, inductance can be defined as knowing the dimension of the core, etc., cross sectional area, mean flux length L, and the permeability of the core, and knowing the number of turns you have wound to create this inductor, the value of the inductor will be this. And if A is in meter square, L is in meter, and mu 0 mu r in appropriate unit, then you can express this L as a in terms of Henry. That's all we need it. So, this L, of course, we will not draw the core, etc. I will just draw like this. It has got a finite value based on its physical dimensions, and then I am telling that the terminal relationship. See, after all, if this I becomes time varying, then this flux will be also time varying, and if flux is time varying, there will be an induced voltage here. So, let me draw this inductance to remove any doubt you still might be having. That is, suppose this is your inductor with magnetic core, this is the thing. This is L, and this is suppose I, time varying current I am passing. If you are passing a time varying current, flux produced in the core will be also time varying phi t. is not. Flux in the core will be also time varying, because phi is after all can be related with h mu 0. So, I is time varying, so phi t. Now, if a time varying flux links this coil, how much will be the induced voltage in it? Across this, there will be now an induced voltage. The magnitude of that voltage is n d phi dt, is not. N d phi dt is the magnitude of the voltage, that is d dt of n phi. This will be the induced voltage between these 2 points, and I am assuming this wire has got no resistance, pure inductance. So, there will be induced voltage, and here is your supply voltage V t with this plus this minus, and this is the induced voltage across the coil. The polarity of the induced voltage will be such that it will try to oppose this change in flux. If flux is increasing with time, if I is increasing with time, phi is increasing with time, then it must have a polarity this side plus this side minus, so that it can opposes the supply voltage to have any, try to oppose the change in the current value. Therefore, n d phi dt, of which n is constant, n d phi dt is this voltage, then you write n d dt of phi is b into a, it will become a time varying thing like this. Then you write n d dt of b is mu 0 mu r into h, and h is n I by L and A, of which if you take out all the constants. So, this is the induced voltage here across the coil. So, E will become equal to, this n will come out n square, mu 0 mu r is can be also taken outside, because they are treated to be constant, only I is the variable. So, mu n square mu 0 mu r A divided by L. What is the small a? Small a is this mean length of the magnetic circuit. It depends upon the physical dimension of the coil, small l. So, this into d I dt, but we have already defined this to be my inductance. Look at this. So, we write it as L d I dt. So, mind you that L into I, this quantity is the instantaneous flux linkage, instantaneous flux linkage with the coil, flux linkage with the coil. I think we have got a fair idea of an inductor and what is the voltage across it. Voltage across it is L d I dt. L is a constant property of this coil, and it will be expressed in terms of that. If d I dt is positive, current is increasing, then the polarity of this induced voltage will be, this is plus, this is minus. So, all these things I have summarized in this diagram. While representing an inductor in a circuit, we do not draw this elaborate diagram to indicate inductor. Just by coil, you assume current is entering through any point. As I told you, deduction of current assumption is our prerogative. Whoever is solving the circuit, he is free to choose in which direction current is flowing. But once he chooses that and also assumes d I dt is positive, he has to mark the voltage across the inductor is in this way, in whichever terminal current is entering, that is plus, that will be minus. That is the whole idea of an inductor. Okay. So, in case of resistance, we have seen that V equal to R I, that was the relationship between voltage and current, terminal quantities. This is how it was related. In case of inductor, we find this, I will also write sometimes V, as I have told you. V means potential of plus with respect to minus. So we find that voltage across an inductor and current flowing through it is not is equal to some constant L into I, but it is L into d I dt, that is most important. What is the implication of that? Implication of this is, if you know the current value of the voltage, to find out the present value of the current, it will not be of same shape as that of the voltage, because there is d I dt you know. From that you have to integrate and get the value of the current. So, let us try to see what I am trying to tell. Suppose you have an inductor L and you have chosen the current direction like this and this is the voltage, which may be a time varying voltage. Therefore, I know that L d I dt is equal to V. This is always true. My problem is I want to find out the current. So, current, to find out current, so what I have to do? I have to first get what is d I dt. It will be equal to 1 by L into V t, that is all. Then you can write d I as 1 by L into V t dt. Now, to find out the value of the current at any time t, then I have to integrate this to get the value of the current. Now, the question is, what should be the limit of this integration? How do I integrate it? Look here, this point you listen carefully, what I mean to say. This is the time and your voltage waveform, as I told you, could be anything, any function of time. Let us say the voltage waveform was doing like this. This is your V t. This is your t equal to 0, and this side it is t equal to minus infinity, and this side it is going towards infinity, positive infinity. So, suppose let us say that I want to find out, I have applied such a voltage across an inductor and I want to find out the current flowing through it at a given time t. So, at this time t, what will be the current? Knowing the fact I have applied this sort of voltage, whatever it is, V t. Then to find out that current at any time t, I have to integrate this one from t equal to minus infinity to t, and this side also minus infinity to t, is not? This is what I have to do. Okay, this is the integration I have to do. So, what will be this integration? This integration will be I t, no doubt, d I If you integrate I t, you get straight away, and this side you see it is equal to 1 by L, t is equal to minus infinity to t. You have to integrate up to time t. So, sometimes okay, here is t, here is t. Sometimes what people do is this, it is a very scientific way of writing. Suppose d I dt is equal to 1 by L into V tau you write. You want to find out current at any time. So, L d I tau dt is equal to 1 by L V tau. So, d I is equal to 1 by L V tau d tau, and then I at any time t will be 1 by L into t equal tau equal to 0 minus infinity to t v t v tau d tau. Like that also you can write. Anyway, the point I want to make it, this is okay, v t t t. This is the thing. Therefore, current at this time t does not depend on the current value of V t alone, because this, if you want to integrate this V t dt, it means what? It means the area under this curve. V t into dt is nothing but area under this curve, is not? Therefore, to calculate the area under this voltage time curve up to time t, you will require all the voltages, previous voltages that you had applied across the inductance. Unlike resistance, resistance cannot remember anything. Present value of the current is present value of the voltage applied divided by resistance. But for inductance, it is a different ball game altogether. It says that the current at this point, that is I t, will depend not only on the present value of the voltage, that is this one, but also you require to know all the voltages applied previously from t equal to minus infinity, and that will decide the value of the current at time t. Therefore, correctly then inductor is a memory element. Inductor is a memory device. Why a memory element? Sort of memory element. Why? Because inductor will react at time t, how much current it will allow to pass through the inductor. It remembers how you treated the inductor previously, with what kind of voltage, for how long, those integration is necessary. Therefore, previous informations will be necessary to know the current in the inductor at a given time. If you want to know the current at this time, okay, all the area up to that time you have to calculate. So, it looks like a very stupendous task. I mean, what to do? Inductor remembers everything. I mean, how we behaved with the inductor with applied voltage previous to time t equal to t less than t. Okay, that will not be a problem at all, we will see soon, but this is the most important equation one has to remember. So, I stop here today. Please try to understand this equation and the inductance, what do I mean by it, and so on. Only one point I will tell, that if at any point of time inductor, suppose for a wide range of time inductor is carrying a constant current, say 2 ampere current, constant, it is not changing with time. I can at least say one thing, okay, if you are allowing an inductor to carry a constant current, then voltage across the inductance will be 0. If an inductor somehow carries a fixed current, say I, that is which is constant value, which is constant, then voltage across the inductor will be L d dt of I, which is constant, I am telling, does not change with time, must be 0. That means, these 2 points there will be no voltage drop. Therefore, inductor there will be a voltage across the inductor only when the current through it will become a time varying quantity. If this quantity is constant, then I am sure there will be no voltage drop across the inductance. So, more on this topic in our next class. Thank you for listening.